the recording. All right. So again, good morning. And talking about the homeworks, I'm still grading them, and you should be able to see them reflected on Canvas tonight. And finish all the quiz grading as well. We had covered all the materials we need to learn for the Shear. Well, actually, we'll finish that today. So you should be able to finish the homework on Shear this week. In addition to that, we will also start talking about the slab this week and finish the slab on Thursday. And we'll get in the shape ready for the second exam, which is on the shear and slab and irregular sections on April the 1st. That's on the second exam after the spring break. Okay. So we are also thinking about doing a learn in-person lab, Louis. That's where I'm getting at. For the in-person lab, we are talking about a structured design, and me and the TA right now are coming up with a design problem using the software. So I have sent out some requests to students and do the survey about the possible software to use. And I got feedback on RISA, RSA 3D, and that's one design software. And some of the students talking about Autodesk Robot and the SAP 2000. So these are three software I've seen most of the time that people are using right now out there. So let me say it again. So RISA 3D, Autodesk Robot, and SAP 2000. And if you don't have access to neither of these software, let me know. Okay, you should. If you sign up on the university's desktop software, you can find the software for free. All right, but that's the software we're gonna end up using, and we'll come up with a design process later this week, and next week before the break, we'll talk about how we're gonna do the in-person. Well, it's more like a design lab this semester. Okay. Uh, if you have any other interest in the design lab, you can reach out to me by sending an email, and we can talk about in person. All right. But let me emphasize on the second exam here for shear, because shear is very important for our concrete design. So I anticipate a lot of problems on this in the second exam. So you may want to start reviewing the materials right now. Okay. So before I get started, any other question about the course in general or any specific questions for me? All right. Well, if not, let me get back on the shear and quickly let's first see what we have talked about last lecture. So let me hit the shear screen over here. All right. Okay. So everybody see my screen, I hope. And a quick review of what we have done last time, right, about the shear. So we gave it a structure here, excuse me. And the structure have a simply supported condition. And each end, we have to define a critical section, which in our view, it is a distance d away from the edge of the support, and that is the critical section. Okay, so we also talk about what are the critical sections, what are the shear forces at these critical sections, and we ask for how about the center of the support, the face of the support, and of course at the critical sections, which is at left side, distance d away from the support. Okay, and I want to point out again, be careful, right? You do not use the VU max, which is the shear force at the left-hand side support, okay? Instead, we're using the shear force at the critical section for the design, All right, so showing here on the left-hand side is a shear diagram, and we calculated these shear forces at the various sections and labeled them on the shear diagram, right? And the game was last time we talked about the distance or spacing between the left support and these critical sections, right? We label them here at the end of it, okay? Excuse me. And now looking at this shear diagram, right? We said there are two possible design pathways. First is that we assume that the VU critical is right here, distance d away from the left-hand side end of it. And we say that, okay, how about we just design for this? universally across the half span, right? And again, this is showing the left side of the half span here, okay? And then we find out that it's too much, right? As this shaded area showing that this is too much resistance than needed. What does it mean? It means that if I design for VU critical, I'm going to end up with this excessive of a shear resistance that is not needed. That is not needed. Okay, excessive shear resistance that is not needed. All right, so that may be an issue here. That may be an issue here. All right, now what if we do a different way? We do a step approach that we get these shear forces labeled here, get the shear force label here, and do segmental design. That means at each different values, we define a design shear force and provide the spacing correspondingly, and then provide different spacings across the half span length, right? So this would definitely have a less of over design area, meaning that we have a better economical side of the design, right? And what values to pick? What value to pick? So first of all, we're going to pick the value that does not need any stirrups or only need a minimum amount of shear reinforcement, right? So that presents itself phi VC divided by 2. PVC divided by 2. That's the region where we only need the minimum amount shear reinforcement. Moving up a notch, that we can also provide a PVC, where we can use the spacing requirement we did before in the previous lectures, right? And then we're going to move up to VU critical, and that is the design shear we talked about, right? At the end of the design spectrum, we're just going to left with this VU face, right, at the support to be the design shear force across the segment 4 and 5. And the only difference that we have 4 and 5 is that we might end up with a 4 lambda square root f prime c bwd as one of the criteria, and 5 lambda square root f prime c bwd. So we have to see which is which. Which is which. All right. Now we have covered how to design these shear forces, how to design for actually spacing for a given VU. Remember from previous lectures, we covered that. But I'm going to show you a little bit more specifics on how we design them, right? How we design them. So today, let's continue this part. Say we're going to design web or shear reinforcement. Okay, we're going to design web or shear reinforcement for the beam, for the simply support beam. But let's try a very challenging section, say T section. Okay, let's try a T section. All right. All right. So what T section looks like, this is what it is, right? So we have a cap here, we have a web here, and the width of the flange, is 36 inches. Width of flange is 36 inches. And the height of the flange is 3 inches right here. Okay. Now I have several bars at the bottom of the web right here. Okay. And these will be called AS. Right? And let's just say we'll provide this AS later. But now, since this is not a flexure, right? So it doesn't matter for us. It doesn't matter for us. But for the sake of simplicity, let's just say it's a 3 number 9 bars. All right. It doesn't matter for us, but let's just provide it. Okay. 3 number 9 bars. And the width of the web here, BW, is 12 inch. That is the width of the web here. BW is 12 inch. And the total height of the beam is a depth D, and you notice DS, equal to a 24 inch. And a concrete cover here is equal to 3 inch. Concrete cover here equal to 3 inch. This you see B here bottom, okay? All right, so in terms of materials properties, we have a concrete compressive strength of F prime C 4 KSI, and the yield strength of Fy equal to a 60 KSI, right? So this is the section we're going to design for that simply supported structures here we just talked about, okay? So that means if I cut the cross section out, what you see here, AA, is a T-beam, like what we just showed earlier, okay? All right, so that is the structure. That is the structure we're designing for, okay? All right, so here, right, how we're gonna do it? First of all, we say now we're going to design for shear. So design for it. And VC, right, is the concrete contribution. So I want to find out VC first. VC first. So what is VC? VC is the contribution by concrete. That is 2 lambda square root F prime C BWD. And to bring the number in, I have 2 and lambda equal to 1.0 since it's normal weight concrete, okay? Normal weight concrete. Okay, usually, and please be careful here, usually if we don't specify in the exam, lambda is always 1.0 for normal weight concrete, unless it's lightweight where it's 0.75. All right, unless it's lightweight where it's 0.75. So 2 lambda multiplied square root of 4,000 psi and multiply BW, which is 12 inch, and multiply D, which is 24 inch. Right? So I got this number to be 36.43 kips. All right. So VC is the contribution by concrete, right? And naturally, I want to find out VVC, right? I want to find out VVC, and that is 0.75 multiplied by 36.43 kips. So this gives me a number of 27.32 K. Sorry, kips, KIPS, right? Kips. All right. So what do we need this for? Why do we need VVC, right? So going back to this diagram here, simply is we're trying to find out the location of VVC first. Trying to find the location of VVC first. We already have this. We already have this. And we also have this, right? So all we need is to find out VVC and half of VVC here. So for the sake of simplicity, let me just put this diagram right here, copy it, and paste here so you can see it visually. Okay, you can see it visually. Let me make it a little bit bigger. All right, right? So essentially, we're trying to find this distance, a distance, right? A distance x away, distance x away from the midspan, from the middle span, right? So let's call it x1. Let's call it x1. All right. Okay. So how do we determine this distance? How do we determine this distance? So VVC using the triangular shape. So VVC divided by x1, that would equal to a VU critical divided by 7 feet, 7 inches or 7 feet. Let me see here. Yeah, 7 feet. Okay. All right. So where's the VU critical? Here. And this is 7 feet. All right. So now bring into the number here. So that is x1, manipulate a little bit, equal to VVC, and multiply 7 feet divided by VU critical, and VU critical is 63 kips. Okay, so I got this number to be a 3 feet. All right, so that means here VVC is located at a 3 feet away from the midspan, All right, so now I got to know where the VVC is. So naturally, next step is find out where half of VVC is located at. Half of VVC is located at, right? So now I have VVC divided by 2, right? So divided by x2, right? Let's just say it's right here, x2, and you can almost directly read it out. It's 1.5 feet, right? And to just run through the calculation, show you here. So that equal to VVC divided by x1, right? So VVC divided by, 2 is located at 1.5 feet. Very simple, right? 1.5 feet. Okay. All right. So that is where we have, the software is, okay, where we have the half of VVC. So why do we need this? Why do we need this? Again, let's get this diagram cleaned up here and show you again why do we need this. So here is my half span, okay? And let me try to draw the full picture out clearly to you. So this is simply supported condition, and that is the full span. That is a full span, right? And the shear diagram definitely reads like this: a triangular shape has a maximum at two ends. Please mute yourself. And then I have the half span to take care of because it's symmetric, right? So this gives you the half span shear diagram like this. Okay, half span shear. Oh, so slip through my hand. Okay, like this. And we say this is the middle of it. So this is 0, right? 0, x equal to 0. And this is force is 0 as well. VC is 0, sorry, VU is 0 here as well, okay? And then as you're marching away from the middle span, I have a 1.5 foot, right? Here is where phi VC divided by 2 is located at. Phi VC divided by 2 is located at, all right? And if I keep going a little bit further, keep on going a little bit further, and this now, ladies and gentlemen, is where the 3 feet of phi VC is located at. Okay, right? So let me just put the number here, 27.32 kips. And this is 1, 3, 6, 6 kips. Okay, 13.66 kips. And then keep going. I hit my VU critical, that is, where are we? It's 63 kips. Okay, VU critical, that is 63 kips. And go here, here, and then, oh, here. And this distance right here is 7 feet. All right, this distance here is 7 feet. And then I keep going, right? I keep going. I say VU, right? VU face. This is at the support, equal to a 81 kips. 81 kips. All right. And then at the end of it here, I have the maximum shear force, VU max, that is 85.5 kips. 85.5 kips. Okay, so finish the distance here. So this is 7 feet, and then this distance right here is 9 feet. Okay, and this distance right here, the total half span here is 9.5 foot. All right. Okay. So now this is my shear diagram, and to be more specific is that I'm going to label this. I say this is my design shear diagram. And folks, I want you to pay attention to this. Okay, this is my shear design diagram. Okay. All right. So why do I need this? Why do I need this? Because I want you to design my shear, right? Design my shear in terms of web reinforcement spacing for these sections, And I'm gonna say, I want this to be region 1. This is 2. This is 3. Okay. This is 4. And this is 5. Okay. Different regions, 5 regions. All right. So this problem become a design spacing problem. Hence, for our quiz, okay, for our quiz, and this is for you, okay, I want us to provide stirrup spacing for these 5 regions. 5 regions. Okay, and to be more precise, that is to get us spacing for, and let's just assume at number 3 stirrups. Of course, 60 KSI of yield strength. Okay, that is FYT, 60 KSI. Okay, so essentially is the spacing for 1 VU equal to 13.66 kips, 2 VU, and this is VU, okay? VU equal to a 27.32 kips, okay? And number 3, VU equal to a, let me check, 63 kips. And number 4, VU equal to a, what's the number? 81 kips. And number 5, VU equal to a 85.5 kips. All right, so I want you to design for this. If you were asked, Bob, I haven't seen this before. Oops, we have a problem, right? You should have seen this in the previous lectures, right? So if we go back to lecture 14, remember? We go back to lecture 14, right? And this is what we had, remember? This is what we have. We keep increasing the VU and asking you to find different spacings, remember? But the only difference is back then we're designing for a rectangular section, and now for this problem, ladies and gentlemen, we're designing for a T section. So you may ask, look, Bob, it's T, it's not a rectangular section. Now I will just tell you, ladies and gentlemen, here B width will become 12-inch of a width, and the depth D will become a 24-inch of depth as we talked about before, and nothing changes as jumping from a rectangular section to the T section. All right. Okay. So that is the quiz. That is the quiz number 8. Okay. Quiz number 8 for you. And then when you finish the design, when you finish this design, you will see that hopefully, okay, I can show you that hopefully this will be the pattern of stirrups that should look like, right? So 2 stirrups maybe here, a little bit more denser here, a lot denser here, okay? A lot denser, very dense, right? Here and here, okay? All right, so you have different stirrups spacings in these regions, different stirrup spacing in these regions, all right? Okay, so I'll review the answer next lecture on how the spacing should look like, and can we even simplify them, right? Can we even simplify them? Okay, so this is the shear design, all right? Okay, so I'm gonna pause here since we have covered all the shear design problems. Any questions for me on this section, folks? Anything on the shear design? Anything? All right. I'm sure you'll ask me tomorrow, Tuesday office hour, since we're a little bit in the weekend mode. All right. But please digest this because you need this for your homework as well. Right. You need this for your homework as well. Okay. And the main thing that we have added on top of the lecture last time is this shear diagram. And you use this in the exam number 2 as well. You need this for exam number 2 as well. Okay. All right. Okay, if no more question, let me start the next lecture. Okay, which will be lecture 16, all right? So let me just try to get this right. So lecture 16. And we're going to talk about one-way slab. I don't think I can finish that, but at least we introduce the concept to you, okay? All right, so one-way slab. Let me write down here. So lecture 16. One-way slab. Okay, now when we talk about slab or one-way slab in this case, it is actually the flexure design that we're interested in. It's not shear, okay? It's flexure, still bending, okay? We're going back a little bit on the flexure again, all right? And the reason why this is different from the beam, and we'll show you, is that because the low depths, shallow depths, and service conditions, okay? Because the slab has different function than beams. So there are a lot of requirements that is different from the beam. We'll talk about them. Okay. So the objective of this lecture today first is that we shall be able to describe. Oops, my red tab's horrible. Describe the conditions, right? The considerations. Okay. The considerations for designing a one-way slab. That is almost the way to say that definition of one-way slab. Okay, definition of one-way slab. All right, the second thing is that we ask you guys to know how to determine, the area of reinforcement. Okay, this is a different concept now, area reinforcement. All right, provided in the unit strip, That's another new concept here, unit strip. All right, let me just emphasize this, okay? One-way slab, unit strip, okay? And this is given the bar size, we'll tell you what bars we're using, okay? Given the bar size and given the bar spacing as well, okay? You might be very confused right now because you know the size, but what about spacing? What you're talking about for flexure reinforcement? What are you talking about? There's no spacing for flexure reinforcement, right? Let's talk about it. And then last but not least, we want you guys to know how to design a one-way slab, per with respect to ACI 318.19. Okay, basically design for it. All right, so first of all, what is one-way slab? One-way slab. Well, you say, Bob, that's easy, right? I mean, just a slab running one way, one direction. Well, I know, right? Well, I know, but how do we define it as one way, right? How do we define it as one way? Why can't we say it's two way, right? So first of all, the definition that is a large flat plate or RC plate, right? Reinforced concrete plate supported by beams, walls, structures in general, right? Structure steel, beams, hybrid, you know, for example, all kind of things. All right. So that's the verbal meaning, right? To have a picture in my head to say this is one-way slab, this is the simplified drawing. That is, if I have a simply supported condition, now I'm drawing a 3D view, okay? I'm drawing the 3D view. If I have a simply supported condition, that means my left end supports like a rod, like a roller, remember? Like a roller here. And then I have a simply supported. Now, when I have a triangle, that means two-way fix. This is one-way fix. Oh, one-way fix in this direction. Okay. And then this goes like this as well, a triangle, like a chocolate bar, right? And then this goes here like this. And it goes like that, right? Okay, so that's the two supports, right? One-way slab defines as a plate that I'm sitting on top of it, deflect predominantly in bending, and like this in the curvature shape like that. Okay, so that is the one-way slab. All right, that is the one-way slab. So forgive my drawings. I'm trying to draw the shape as accurately as possible, but that is what it looks like. Okay, so this is the one-way slab, and I can say the height of the plate is called HF. All right, and the span length Span length between the support, span length between the support is L1, L1, okay? And why we call it one way? Because this is the predominant, the bending direction, the bending direction. There's another span going this way, right? There's another span called transverse span, and that is L2, L2, okay? So I'm gonna call this longitudinal span direction, okay? And please remember this, okay? Longitudinal span direction, and this is transverse. Oops. Transverse span direction. Okay. L2 is transverse, L1 is the longitudinal. Okay. All right. So I call this one-way slab only if it is a one-way slab when slab bends predominantly along a one or longitudinal direction. Oops. Okay. All right. So this is the first very important concept because we call it one way because it bends one way, only deformed like this. Okay. In another direction, it does not bend. It does not bend. It just follow the shape. Follow the shape. All right. And the second thing, very important as well, is that this, when we design the slab, right, plate, of course, we will design it as a bending, right, as a bending this way, but we only have to take a small portion out of that. We're going to do a cut. Okay. We're going to do a cut, something like this, right? And we're going to cut a unit strip that is 1 foot. We'll do a 1 foot. Okay. So everything we do, everything we design, we're only designing for a unit strip. Unit strip means 1 foot in L2. Okay. 1 foot in L2. So essentially, if we design a one-way slab, we only need to take a 1 foot strip and design for it and assume it's universally true across the transverse span direction, across the transverse span directions. All right. So this is the definition of one-way slab and how we design for one-way slabs using a unit strip. But there are strict definitions of one-way slab, right? And I said here as only a qualitative way is that it bends predominantly along one or longitudinal directions. But how you quantify that, right? Bob said, give me a number, right? How do you say it's a one-way slab for sure, right? I need a number. I need to characterize it. So here is the number we're going to use. When we have, right, L2, that is this direction, L2 is larger, of course, than L1, and is larger than L1 by 2 times or more. Okay, by 2 times or more. Okay, and this is called one-way slab. One way. All right. But if I say my L2 over L1 is in between 1, sorry, smaller than this and bigger than this. So between 1 and 1.5, and this is two-way. Okay, this is two-way. So what exactly are we talking about, right? So here is the situation. When we have one way, right? I want to take a look at the top view. This is 3D view, so how about top view? Right? So one way essentially is like this. And since it is bending in the L1 direction, okay? And my drawing is a little bit imprecise. It's not right. So let me just redraw it a little bit. Apologize because I want to do the ratio correctly, okay? One-way slab top view, meaning I have a longer side, this side, and a shorter side, this side. Okay, so this is my L1, and this is my L2. Okay, and when I have a one-way slab, right, what I really hope for is that I'm going to divide my slab into two ends. Now, this is if it's continuous, if continuous, not simply supported, okay? If it's continuous, right, I can divide my moment into negative moment zone and positive moment zone like that into strips. So this is one-way slab. So coming down to it, we call it one-way because we only have to worry about the moment distribution in one pattern, right? One direction. But if I have a relatively square shape, all right, when I consider my moment, I have to consider a failure line, okay, which you will learn later. A failure line, so let me use red to differentiate here, and 45-degree angle, crack line here, crack line here, crack line here. And the shaded area is the new so-called bending zone, okay? All right, and in the middle is my positive bending zone. So this is L1
Professor, I have a
direction.
question.
Yeah, go ahead.
Whenever you have L2 over L1 there, are you saying the ratio or are you saying just if L1 is two times greater than
Ratio,
L1? Okay,
right? This
ratio
is,
of.
let me
Okay.
just, sorry, I used to write this way, but essentially it just does, right?
Yeah, I just want to make sure because you had just
Right,
said if L2 was two times greater than L1. So I just
right,
wanted to make sure.
right. So it's just ratio L2 over L1 bigger than 2. Sorry, I should have said this bigger ratio is bigger than 2. Okay, all right. So this is again if continuous, or we call it integratedly. Integrated. A lot of words I'm throwing out today, and don't be terrified. Okay, I will explain. If integrated, and we'll talk about this. And this is two-way. Okay, all right. So the main concept, the main difference between the one-way slab, two-way slab is the moment zone. How we differentiate the moment. How we differentiate the moment. Okay, all right. So now, of course, in our course, in this class, we only care about this one-way slab. Now, for this, we're not covering in this lecture, but there will be a cover in the advanced section of the reinforced concrete design, okay? In advanced reinforced concrete design, all right? Okay, all right. This is not all the drawings you're gonna see, actually. This is not all the drawings you're gonna see because I want to be more specific, right? So let me even expose this one-way slab structure more clearly to you, okay? Let me explain it, right? So here is the situation. I'm going to have a structure and I want to draw a top view of a one-way slab again in detail, meaning I want to show you the support. I want to show you the support. Of course, a plate, right, need to be sit on something, right? It need to be sit on something. So first of all, I'm gonna have a beam, main beam going this way. I'm gonna have a main beam going this way, right? And let me call it bay one. Okay, so you can imagine some beam sitting underneath it, right? Bay one. And I have another beam sitting in this way, and this is main, okay, big beam. And let me call it bay two, bay two. All right, and of course, equally spaced, I have the third beam sitting here, bay three, right? And now to get this beam in support, right? To support all these beams, naturally, I need to have some cross beam to support underneath it, right? So I'm gonna draw the cross beam sitting underneath it here, and dash line here, but straight line here, dash line here, straight line here means it's underneath it. You don't see it, right? So that's the cross beam underneath it, right? Same thing here. I have a cross beam here, edges here, and then dash line, solid, dash line, solid, dash line, solid. These are the beams underneath it. Okay, but if this is not enough, right? I also have this short beam poured together with this, poured together with this, right? And these small beams extended directly to the slab itself, extend directly to the slab itself. Okay, and these are, I call it 1 prime, 2 prime, right? And etc. So on and so forth. So just don't have to worry about this, right? We'll just cut it off right here. So to simplify. Okay. Sorry, I'm trying to draw as clear as possible, right? This is still ugly drawing, but anyway. Okay, so you see immediately, right? I have some overlapped column support underneath it, right? I need a column underneath this transverse beam here, right? So where the shaded area are the columns, right? Shaded area are the columns. Okay, and then in the transverse direction, of course, I call this A and I call this B. So that is more detailed drawings for the one-way slab, right? Now, I need to show you the directions, right? What are the one-way slab directions? So use red color here, and you notice that if I do the center of this beam here, center of this beam here, you start to see that I'm not going just from the main beam, right? This 1 prime is still considered as a beam, and this is L1. That is the bending direction. All right, L1. And this between A and B, this is L2. The transverse direction, this is L2. All right, this is L2. Okay, so of course, to call it one way, remember L2 over L1 has to be bigger or greater than 2. Right, bigger, greater than or equal to 2 to call it one-way slab. All right, so that's that. So where is this strip, right? Unit strip we're talking about, right? Where is this unit strip? The unit strip, right, is basically a cut of strip just like that. Okay, I'm gonna shade it. Cut of strip like that. And this width is 1 foot. Okay, and this, ladies and gentlemen, is the unit strip. My spell today is horrible. Unit strip. Okay. All right. Now, one more thing. Okay, so this is unit strip, right? It's a unit strip. And then I want to put it here. I say, okay, you're talking about a continuously supported beam and have a L1 direction and supposedly will bend like this. Yep. And you have a unit strip, right? So if I do a cut and I want to show the cross section, what do I see, right? What do I see? So if I call it AA, section AA, what you see here should be a unit strip of a slab, and the height is HF, and this is 12 inches or 1 foot, and you have spacing at the bottom. All right, and this is at AA, right? AA is in the middle span, And don't forget, this is L1, okay? What if at the support, BB? Support, well, we have the same geometry, right? So it's gonna be HF, which is the height of the slab, and width of it, 1 unit strip, 1 foot. Okay, but what is difference? BB is right here, somewhere here, right? Well, actually, let me just cut it right here. BB, AA is here, right? So for BB cross section, it is under negative bending. So this is at end span, negative bending. So the reinforcement or the AS is on top for negative bending. All right. So why are we going through all this? Why are we going through all this? Because we are going to talk about how we design for the reinforcement for the top and bottom negative and positive bending moment. Okay, positive and negative bending moment. All right, I got 5 more minutes, so let me just quickly mention one quick concept. Okay, so this is how we're going to design for it, right? So quickly, we have L1, L2, and determines the one way by using L2 over L1 ratio is greater than or equal to 2, and then we call it one way. And we cut the different cross sections, right? Here in the middle, we have reinforcement at the bottom. Here at the end, we have reinforcement at the end support. Okay, so this is how we're going to design it. And so we're going to call a new concept is that for web, right? Since this is 1 foot, 1 foot. So we are going to determine how much reinforcement we put in this 1 foot distance. This is different from the beam because in beam, we actually have a width. So we have to come up with equivalent reinforcement concept that is AS, okay, AS per foot, okay, AS per foot equal to the AB, which is provided reinforcement area, okay, well, actually, let's call it, well, AB here, AB here, okay, and multiply by 12" per S, okay, so this is a spacing, okay, this is spacing. All right, so we have to normalize it. We have to normalize it. All right, okay, so next lecture we'll talk about how we're going to normalize it. All right, so this is where it's good stop. So I will stop here and pick this up on Wednesday. If you have any question, you're welcome to stay and we can talk about more. Okay, and just for the sake of curiosity, one of the students asked me, or actually two of them asked me in the exam number 1, say, look, Bob, you have section A, which is positive, so bars at the bottom. You have section BB, which bending moment is negative, the bars on the top. How do you make the meets end, right? How do you transit between the top and bottom? So quickly, if I have a beam, right, I want to look at the sideways, right? This is just curiosity and you don't have to know this. We'll show this in later lecture. But if I have a simply supported beam, I don't have this issue. But if I have a middle support, right? And I know that the bar is going to lay at the bottom here for this end of it. And then I have a positive bending moment here, but I have a negative bending moment here. So what I do is I'm going to put both top and bottom like this. Okay. Right. So this is one design approach. I'm just going to lay the bottom reinforcement continuously and lay the top reinforcement only into the segment that has a negative bending. Okay. Negative bending. But be careful, I need to extend it to a certain distance, and this is cutoff distance, meaning that this is the bar need to be developed to reach my yield stress. Okay, so that's one way for design. The other way, if I were being clever, I can do this, is that I can get the bar like this, go down like that, and then go like this. Okay. Okay, so I can also use this to transit between the top and bottom reinforcement. All right, just some thoughts for you, okay? Just some thoughts for you. All right. Okay, well, thank you very much. I'm done with today's lecture and I'll see you on Wednesday. All right.